Thank you very much, Igor, for the nice introduction, and thank you for being here. It's actually a pleasure for me to have the opportunity to tell about a topic that is very dear to me, which is trying to have a developmental perspective on cognitive robotics for interaction. And you might ask, why should we care so much about interaction now that we see all these technologies so advanced, these robots growing better and better? Do we need it? It's already solved? And the answer, unfortunately, is no, because despite we have witnessed an increasing ability of our robots to move better, of our general AI technologies to think in certain fields better, when it comes to interaction, we still face terrible failures. And that's a bit paradoxical, if you want, because on the one hand, we have these very incredible systems that in some fields are better than the most advanced adults. And then, yet, when it comes to understanding each other, well, they fail the comparison with young children. Young children are still much better. Why is it so? Well, a big problem is that we do not share the same perception with robots. So machines are designed to be as accurate as possible. Humans are not. Humans see the world in a different way. They understand the world based on their own experience, which is something that machines don't really do. So this is the classical example I make. If I show you this picture, what the little robot would see in such an instance, this is the iCab robot, well, it could see a movement, an object, and it could track it maybe very precisely. But what you see is so much more. You are seeing the intention of Carlo to pass the plush to the robot. You see also the disposition that it's showing to the robot. You may imagine he's not going to slap the robot soon. You also notice that he's handling carefully an object. Well, this is something that your brain immediately captures without you consciously thinking it. And this allows you to be prepared in advance and to adapt very easily to the need of your partner. Our machines, even our beautiful iCab, can't yet do that. And why do we have this advantage? Well, because we are designed to do so. One of the most paradigmatic examples is that of the mirror neuron system. So areas in our brain that are active both when we are performing an action and when we are observing someone else performing the same action. This provides us with a sort of vocabulary that allows us to implicitly understand and predict the others, their intentions and their goals. And that facilitates our understanding and leads to a strong form of communication, embodied communication. What I mean is that each and every of our actions becomes per se a form of communication. And I'm not just meaning gesturing. It means that here, now, while I'm talking, you are monitoring the prosody of my voice, you are monitoring where I'm looking at, you are monitoring how I'm moving around. Your brain is using that to predict if I'm gonna suddenly ask you a question, for instance. So this is a precious source of information that we are continuously processing and that helps us in establishing an implicit communication and also in negotiating shared goals and intention with our partner. And we would love our robots being able to do the same. And sometimes we think it as not so difficult because we give it for granted, because we have it since our childhood. So the very day we were born, we started noticing better biological motion, that motion that was caused by non-biological agent. In the very first days of our life, we are more attentive to the gaze of someone that is looking at us than to a gaze that is averted. We are sensitive to facial expression. And even before the second years of life, we start being able to anticipate others' intentions and show instrumental helping which means that a baby at 18 months can see that you're trying to do something and you're failing, and this little guy will intervene and try and help you. No machine today can do that in such a generalized manner as a child. And so we are bumping into, again and again, what was already seen very clearly in the 80s, so the Moravec's paradox. The fact that the task that to us humans seems so difficult, like doing a backflip or solving chess or Go or StarCraft, are actually simpler to be ported on a machine than those tasks that a 1-year-old child can easily do, which include understanding, predicting, adapting to a partner. So this leads to the idea that, well, maybe coming back to children as inspiration could be a good approach, also for robotics, also for computer science. And this was a line of research that was started quite some long ago, for instance, by Professor Giulio Sandini, who started experimenting with child-looking robots, first very robotic-y, and then with the starting of the RobotCAD project in 2004, there was really the idea of building a platform that was a child, not just to build a robot, but rather to create a new system, platform that could be used by multidisciplinary people to try and investigate how humans learn to learn since their childhood. So the idea was to understanding a very complex system, the human child as well, by trying and building a complex, though simpler, system, our robot. So the robot grew up. Now there are more than 50 iCubs around the world, used from Japan to US to Europe, everywhere, by different people studying different aspects. And 2 of them are actually with us. We work at the IIT in Genoa. This is the Erzarli Center of IIT. And what we are doing is we are using the robot as a tool to understand better humans. Which means that we couple the robot with all the other instruments that we can normally use to study humans, be it motion capture to investigate the kinematics, be it eye tracking, be it a sensorized object to study human-object interaction, be it neuroimaging. Well, we couple that with the use of the robot, because the robot is a controllable agent. I can control what it does, I can control what it perceives, I can control what it decides, and it can interact with me. So at the same time, I bring the controllability to the field of interaction. And the interesting thing is that this becomes, if you want, a puppet to try and study the human in a controlled way, but then we can also use it to develop algorithms that start from the models that we have studied on the human, and then bring the similar capability onto the robot. So to recap, our ambition is to create a cognitive architecture that enables the robot to adapt over long-term interaction to a human. To reach that point and build the cognitive architecture, there are 2 important steps that we need to take. And one entails understanding the sensory, motor, cognitive basis that makes us humans so incredibly good at interacting with each other, and building, taking inspiration from this model, analogous model that can also be strongly based on AI system onto our robots. For instance, to make it good enough to make use of those embodied communication signals that we were discussing before. This is a possible pathway to bring developmental robotics to the study of cognitive robotics for interaction. And in the following part of my talk, I would like to give you some practical examples of what kind of research you can imagine doing within this pathway. Starting from the basic, We want the robots to be sensitive to those signals of embodied communication that we know matter so much for human-human interaction. And we want to start simple. And what's the simples? Newborns. As I told you, newborns are immediately able to detect whether something moving in front of their eyes is moving because it's animated, is biological, or not. We don't know exactly how they do, but they do. So what we did with some computer scientist fellow was to try and allow our robot iCub to do the same. So without a priori knowledge, so not knowing the shape of a human, not knowing anything, but just looking at something moving and detecting like the velocity and the curvature of the motion, allowing it to detect whether it was biological or not. And it worked. The robot, after a little training, was able to do that. And the beauty of that was then by using the very same principle, so very simple geometric extraction of velocity, curvature, simple properties, no a priori knowledge, it was possible to the robot to do also more complex tasks, like understanding action across different views, or coordinating with a periodic motion. And more recently, we found out that the same subtle feature of the motion, velocity and curvature, could also reveal something of the object that is moved. When we are moving a sturdy object or we're moving a fragile one, we move it differently. Our brain optimizes for it, we don't care, but naturally our movement changes. And as an observer, I immediately realize if you're handling something fragile or not. We wanted this ability also on our robot. And we found out that reusing exactly the same feature, it was possible for the robot through its cameras to detect whether an object was fragile or not, knowing nothing of the object, just looking at the motion. Of course, movement is just one of the many multiple signals that we can use to understand someone. We, of course, leverage also on facial expression, and our robot has the ability, has developed, let's say, the ability to detect facial expression. We could detect, let's say, the style of an action also without looking at the face, but just looking at the way a person is moving. And we humans are so communicative with our bodies that we can even detect the emotional state of a person just looking at how this person is manipulating a sensorized object. So this that you see here is a little cube, it's called iCube, and it reports information of how it is touched on its surface and how it is rotated. For the moment, not even the pressure. Well, just by looking at this information during a passing action, it was possible for us to detect whether a person was moving aggressively or kindly, or whether it was this person was expressing a high arousal state or a lower arousal state. Another very rich source of information is the gaze. And originally we started using the gaze as an information relating to the goal and the intention of a person. And we found out that it's extremely actually communicative. So we made the robot blind to anything else. The robot could only see where the person was looking by combining head and eyes information, and had to convince either the robot or an experimenter to pass. So the participant had to ask the robot or an experimenter to pass an object. And we found out that the robot, being able to see only the gaze, was able to guess the right time to intervene and the right object to pass in most of the time. This told us that this information, though scarce, was already very effective. And we didn't have to teach the participant. Participants actually interacted naturally, smiling, talking, pointing, but their gaze alone was enough to collect and allow the robot to guess. The head information alone was good, but not as good. Then we found out that beyond gaze direction, there are other precious information hidden in the gaze of a person. So if you look at the pupil dilation, for instance, you have a very good measure of the cognitive load that a person is experiencing. That we know from cognitive science, we didn't know whether this is something stable enough to be used in a real and actual interaction. And so we created this architecture in which the robot is creating a game. So the participant sees a lot of cards with funny drawings on top of them, and the task of the participant is to either describe correctly the drawing or to invent a story, lie about the card. And the robot has to guess on which card the person is telling the truth and on which card it's creating a story. And we found out that by using pupil dilation alone, the robot could guess more or less 80% of the time, which is much, much more than the human equivalent. We can guess around 54% of the time. So again, another evidence that this subtle information are really quite strong and informative for an observer. And we found out also that if we don't consider one signal at a time, as we did so far to study the power of each signal, but we start integrating multiple sources of information, then our ability, or better, the ability of the machine to understand and predict becomes much better. So we found out that by combining physiological measures like heartbeat together with the pupil dilation, we could have a sense on whether a person in front of a risky scenario was able to understand the risk, and even whether this person was going to face the risk and accept the risky proposal or not. Or combining information related to the gaze, the face position, and the body position, we developed a system that was able to understand the comfort, or better, comfortability of the human in interacting with the robot. So not exactly which emotion the person was perceiving, but rather if the person was engaged and desired to continue in interaction with the robot, or maybe the robot did something wrong and the person wanted to go away. Again, by combining multiple sources of information, in this case the pose of the body and the face, it is also possible to solve complex tasks like the addressee detection. So understanding who is talking with whom, which is particularly difficult if you're not in a dyadic scenario and if you're in a natural scenario where maybe the robot is not the target of your attention. The combination of these two information proved actually to be significantly more effective than using either one or the other. So far I just gave you a stroll throughout the large number of signals, and they are not all of them, of course, that we continuously as humans use to make sense and predict the others, and that a robot could use either in isolation or combined to gather itself a sense of the partner. But this is not enough, because there is a problem. The problem is that if you really want to understand a human, you have to realize that their perception, our perception, is different from a machine perception, is not accurate. So our perceptual process is an inferential process. This means that I take the information that comes through my senses, but then I add something. I add my prior knowledge to actually ensure that my comprehension is better. This is happening all the time. We realize that it's happening when it fails. So this is the case of the visual illusion. What our brain is doing is actually trying to fill in the gap in our perception. But this can bring perceptual distortion. And this applies to everything. And it applies to the perceptual, so we have perceptual biases, and it applies also at the cognitive level. We have cognitive biases, which means that, for instance, we do not memorize things accurately. we don't trust or rely on information just based on their validity, but we have like egocentric bias. We trust ourselves more than others, even if sometimes it's not the right thing to do. So what we need to do if we want to make robots better at understanding us is to endow them with a model of these distortions so that they can anticipate that they exist. So modeling biases in our perception and modeling biases in our cognition. So again, I want to give you concrete examples about that. So we focused on a specific bias in perception, which is central tendency. This applies to any quantity. So if I ask you to judge time, if I ask you to judge space, well, what you do, you won't give me the right answer, the accurate estimate, but your estimate will be based on your previous history. This means that, I don't know, if I show you 3 long lines, and then I ask you to judge a 4th line, you will perceive it as longer than it actually is. Because your brain has created a prior history telling it that usually lines are long. And interestingly, this significantly changed the way you perceive time and the way you perceive space, for instance. And it's common among all of us, and we don't realize it. Of course, machines do not have that. So what we did was, first of all, to try and quantify this phenomenon. So in this case, we have the robot like showing a distance on a screen with 2 points on a touch screen and asking the person to reproduce this distance, nothing more. And by measuring the distortion in the reproduction, we could move on and really model it. Luckily, from perceptual science, there exist nice models, Bayesian models, that can describe very well this phenomenon. And with the robot, we could first model this phenomenon and also see and quantify how it changes when the person is not alone, but interacting with someone else. So we studied it with space perception, but then we moved on temporal perception. So this is interesting because sharing time perception is crucial for coordination. So imagine you're in a room and there is music, and you're dancing alone to the music, and you can synchronize, you think, very well. On the other side of the room, there is another person. It's listening to the same music, and he believes he's synchronizing very well to the music. What we know, though, is that these 2 persons, though listening to the same music, could be listening to different tempo, exactly because they might have different perceptual biases. So what happens when they decide to dance together? Now their task is to actually synchronize with each other and to the music, which is non-obvious because they have 2 different perceptions of the music. So we wanted to investigate how can we adapt and synchronize so well with an agent that has a different temporal perception than us. And we didn't make the robot dance for simplicity. We had it play drums, practically. So there were 2 lights that indicated the tempo, and that the person and the robot should reproduce the duration of the light by playing the drums. The interesting thing is that we manipulated the temporal perception so that we had the human temporal perception and we ensured that the robot had a different time perception. And this was the task. So the time was actually the time between 2 flash of lights. And your task when you were dancing alone was to reproduce that duration by tapping a 3rd time with a stick. And then we did it. First, the person was doing it alone. Then the person was doing it with the robot, with the idea of needing to synchronize with the robot. Then it's as if we turned off the light. So the person needed yet to synchronize with the robot, but could not see the robot anymore. And last, the person came back to dance alone, to play alone. What we found out was that at the beginning, the person and the robot had very different temporal perception by design. When we asked participants to synchronize with the robot, they managed to do that very well. And even when we turned off the light, the participant maintained a perfect coordination with the robot. And when the robot went away, the person came back to their original temporal perception. So this means that when we are interacting with someone with a different time perception, apparently, we are building our own model of time perception and another model for the other agent. And we use them when we need, and then we discard the other when the other is not anymore there. Good. But what allows us to do that? What happens if instead of seeing the robot doing that with me, I don't see it actually moving? I just see the light and the feedback it gives, but without seeing the robot. So I tell you, there's the robot. It's giving these responses. It has its timing, but you don't see it. Does your brain does the same? So does your brain build an internal model of its temporal perception and keep it aside? We tested it. So exactly same experiment. The only difference is that you didn't see the physical robot actually bumping. The beginning, same difference. The person could actually learn the model of the invisible robot quite well and could actually maintain it even when, let's say, the light turned off, so it couldn't even see the response of the robot, so it learned. But when the person came back to play alone, it was contaminated by the temporal perception of the robot. So, okay. This tells us that in this case, what we did was to modulate my own temporal perception model and not build two different models. This tells us that when we are interacting with someone, this can change our temporal perception. And this can even contaminate our temporal perception when we are not anymore with that person. The other interesting aspect is that the motor involvement, so the observation of the other moving, has a deep impact on how we model our own perception of time. So the movement plays a big role. But on the other hand, sometimes even just the appearance of the robot can be used to tap on let's say, our own bias and adaptation capabilities. So we ran an experiment that was related to the idea of inducing participants to be, let's say, more legible in their movement. Whenever you're drawing in front of a child or showing something to a child, it is well known that you change the way you move. Actually, it is called motion ease. You try to move larger, perform larger, more clear movement. Sometimes you also change the way you talk. It is mother ease, changing your prosody to be more clear. So we wanted to see whether we could increase the drawing legibility of a person just by asking the person to show their drawing to a child-looking robot. And we tested that in two settings, here in Slovakia and in Italy, with two child-looking robots, the Nika robot and the ICAB robot. And the idea is that the participant could draw different drawings from different categories, and the participants did it in two conditions. In one condition, they were drawing for a robot, but they were doing it alone. In the second condition, the robot was looking at them. What we were expecting was that in the robot condition, participants would have made the drawing simpler, larger, and slower to facilitate the robot understanding. And these are the results that we found. So the drawings actually became much larger in the robot condition than in the, let's say, individual one. On the other hand, they didn't become simpler in terms of stroke, and they were actually performed faster. That we believe was associated to the fact that there was an observer, maybe some peer pressure to be faster, to make the experiment last shorter also for the robot. The other interesting outcome was that we measured the perceived closeness between the robot and the participant from the participant point of view before and after the interaction. And we found out that the more participants felt an increased closeness with the robot, the more they actually enlarged their drawing during the task, suggesting that indeed sometimes it's sufficient having a certain appearance and a certain attentive behavior to actually trigger some of the basic phenomena of human-human interaction that make it so easy, for instance, for children to apprehend from us. So this was more related to the sensory motor aspect, but as I told you, we also suffer. We have also several cognitive biases. And on this respect, I would like to touch a bit upon the topic of trust toward the machine, which was also one of the main topics of the summer school that was organized. So usually when you think of trust in automation, the main element that define it is the performance of the machine, its reliability, and its transparency. So if we consider pure trust in automation, this should be the pillars that should predict whether I trust or not a machine. On the other hand, if we look at how trust develops in human, we know that that's not the whole story. A lot of other elements play a role, like social norms or reciprocity, like I trust you because this way you'll trust me more next time. So our question was, in robotics, in HRI in particular, where do we stand? Because robots are actually machines, but the way we interact with robots, well, make them in a special niche. So to address the issue of reliability and transparency, we ran a simple experiment. It was a game. We asked participants to come in the lab and to solve a treasure hunt game. We hid objects in the lab, there were eggs, and the robot could give hints to help the participants to find the eggs. And they got a reward, so if they managed to find all the eggs in the fixed time, they won a sum. Interestingly though, the robot, when the experiment started, also told, well, you know what, if you find everything, you win, yes. Okay, you win, very good. I suggest you to gamble. If you find an additional object, then you'll be able to double your earning. But if you don't find it, you lose everything. So my suggestion is that you should gamble. So what we wanted to see was, first, during the game, behaviorally, whether people tended to rely on the robot suggestions or not. And then at the end of the game, we wanted to see whether they complied with the risk of, gambling what they earned. So we saw a large variability in people. Some people wanted to play alone, some people relied a lot on the robot suggestion. But what we could see very clearly, even if the interaction lasted less than 30 minutes, is that already during the game there was an increase in behavioral signs that suggest a higher compliance, a higher reliance, and higher desire to ask for hints to the robot, closer distance. When we went on looking at whether they decided to gamble or not, well, of the number, the subset of people who actually managed to find all the objects in time, 100% decided to gamble. And when asked whether ICAP did play a role in their decision, the majority said that yes, this had a weight. But you might say, well, the robot actually gave good hints, and it was pretty reliable. So why should people not believe in it? So we said, okay, let's manipulate that. Let's run the same game, but now the robot will break in the middle of the game. So we created some crashes. So the robot started moving abruptly, the robot was literally stopping and restarting during the game. And we recorded several variations of this and then validated online. So we asked the people who participated in the original treasure hunt to see the crashes and asked them, well, what would you feel if this happened during your game? And we picked the distortions that people judged more disturbing. And so from the questionnaire, it emerged that these crashes were really problematic. Then we ran the real study. So the same study as before, treasure hunt, but this time the robot crashed during the game multiple times. And we separated the participants, the 68 participants, into two groups. For some of them, the robot crashed but didn't say anything. In another group, we called transparent, the robot crashed and then gave some explanation, like, oh, my motor broke, oh, my sensor broke, or something like that. Because usually it is said that the higher the transparency, the higher the trust, even in phase of failure. What we found out, so we asked at the end of the game the same questionnaire that we asked to the virtual participants in the validation. And we find out that for the participants who actually played the game, the failures were absolutely not a problem. So they didn't impact strongly any type of trust they had toward the robot. So indeed, there was no large reduction due to failure. And this is not just our finding. This confirms other findings in robotics that show that we tend to trust robots despite overt failures. And what about transparency? Usually you say the higher the transparency, the higher the trust. Well, we didn't find that as well, because we found out that the judgment in the case of the robot that also commented about the failure were actually worse. So these results told us, confirming also existing literature, that maybe the basic tenets of trust toward automation are not enough to explain the kind of trust rapport that we'll build with robots. So we said, maybe we should consider the other side of it. So those elements that we know make a lot of role in human-human trust. And one thing that we know for sure, we also quantified it in children and adults, is reciprocity. Again, I show I trust you, so you'll trust me more next time. And we decided that we want to quantify that and to see whether it holds for robots and computer as well. So we performed the task you saw before, the length reproduction task. So we show a distance, and we ask the person to reproduce the length just by pressing a point on a touchscreen. Why we did that? Well, because we know that humans believe are good at doing that, but we are actually very bad. And we're bad in a predictable way, so we can model that. And we created an agent that could perform the task in a more accurate way than a human. So we had humans that have a certain error in this estimation, and our agents, our robot or computer, actually performed the task in a more accurate way. And the task was designed like that. So I'm the subject, and I'm giving my answer. Then the agent gives its own answer, which I remind you, it's more accurate. And then I can decide where to put my final and conclusive answer, getting closer to the robot answer or not, or remaining away. And in some turns, it's me, I decide at the end, I'm the subject. In some turns, it's the robot or the computer role to take the final decision. And what the participants saw were only points on a screen, but they believed they were interacting either with a robot in another room that they saw before, or with a computer. And what we measured was how much they got closer to the suggestion of the other agent as a measure of compliance, of social influence of the other partner. And what we found was that despite the algorithm was the same, despite both agents were much better than the human, the mean trust was quite low, and significantly higher for the robot, which was surprising because the intelligence there was exactly the same. But that was not only. This experiment allows us to study two types of trust, what I call the implicit trust and the explicit trust. So explicit overt trust is, okay, I said A, you say B, and then I have to take the final decision, so you'll know my final decision, so if I get closer to B. So this tells me how much I get closer overtly to the robot suggestion or the computer one. And then there is the implicit trust, which means how much do I use your response to correct my internal model so that my next answer will be more accurate. Because remember, those agents were better than I was. And what we found out was particularly interesting, because in the computer, there was a good alignment. So people who overtly trusted the computer also learned from the computer. They became more accurate over time. In the robots, there was an inconsistency. So people showed that they were trusting the robot a lot in the final decision, but they didn't learn anything from the robot. So they did not actually trusted or incorporated its knowledge. So apparently, they didn't want to disappoint the robot. And we also exploited a study of reciprocity, and we found out that with the robot, but not with the computer, participants used reciprocal tricks. So when they knew that the robot could have reciprocated their trust, they were trusting more the robot than in those tasks in which the robot could have not reciprocated. So we found out that we have to take care of these biases, because we might have scenarios in which we show we trust the robot, so explicit measure of trust would tell us, oh, yes, it's trusted, but then we don't learn from it because we don't trust it. So it is very complex, and a knowledge of how our biased cognition works, sometimes in our favor, sometimes not, is really helpful if we need to design better robots. So far I described one side of the coin, which is understanding and predicting the human. We want, however, the robot to be able to be understandable and legible to our eyes. So this means I know how you perceive me, so I will decide to move and to behave in a way that it's more easy for you to understand. And it's basics. We found out that, for instance, if you design robots that move according to biological laws, then you reuse basic system of coordination that exists in our brain, like motor resonance. I don't know, you've always experienced, I walk around the road, you walk with me, I speed up, you speed up. No effort on your side, it's your brain doing it for you. We found out that this automatic imitation of speed occurs also for humanoid robots, but only if the robot moves according to biological laws. Otherwise, this mechanism is turned off. But we are not revealing just speed. We are also, as I told you before, revealing the fragility of the object. And it would be cool to have a robot that reveals the same. So we tried to generate autonomously movement in the robot behavior that could reveal the carefulness with which an object should be moved. Moving from very humanoid robot to much less humanoid robot, and even to robotic arms. And we found out that if you find the real trick, so you understand how to generate this movement, this work across different embodiments, it brings effective benefits to the interaction. First of all, because you have, again, automatic imitation. You see the robot moving an object with the care, you start moving that object with care, with no cognitive effort. And we also quantified the benefit. We compared two handover actions, where the robot in one case had a very neutral behavior, and in one case it used this expressive behavior, so changing its kinematics for fragile and non-fragile objects. And we found out that in the second case, the interaction went on faster. It was much more fluid. So taking a little more time and more effort in the design phase and in understanding this mechanism in human motor control can have significant benefit in human-robot collaboration. But we don't care only about object manipulation. Of course, we want also our robot to be good at expressing other aspects, like if something is imperative, urgent, or if something is normal and calm. Our brain is actually designed to do that. We have the dorsocentral insula of our brain that responds to recognize these action styles. It's very important for our survival. We want the robot to be aware of this in its motion. And so we started to design how to make it so that the robot could express like aggressivity or kindness in the simplest of its motion. It was absolutely not easy to find the signature in the movement that reveals that. But if you do it right, then you can demonstrate with the fMRI that the same area of the brain activates more or less in the same way for the observation of a human action style and of the robot action style. And this is super cool, because it means that if you design well your movement, your robot movement, you can tap into the very same circuits that make human-human interaction so effective and understandable. And again, it was not easy. It's not just, making a movement faster or slower. With the robot, we could try that, very simplified motion. Only if you capture the real signature of the movement, you can hope to have this neural activation. And this has also behavioral consequences, because you have affective contagion as well, which means if I'm pointing to this object in an aggressive way, you'll pass me this object in a more aggressive way. And we proved that not only with our cute humanoid robot, but also with the manipulandum, so with a physical interaction with a robotic arm that gave either a kind or an aggressive perturbation, and we found out affective contagion. So the next time I had to move, I moved more aggressively or more kindly. And if you're curious about why biological motion and these properties are so important, not only in neuroscience, but also in robotics and in computer science, I suggest you this book where we collected a lot of contributions, and I think it really provides a multidisciplinary kind of perspective of why it matters. So, as I told you, this kind of studies that I've showed you so far are actually the basic building grounds for making our robot go further, become adaptive, become autonomous, which implies, well, for starters, to combine all those signals that we have analyzed separately, to combine all those models that we have proposed in a separate way, and then first, unifying action and perception, but then starting to thinking beyond that, because for a cognitive agent, we need also memory, we need learning, we need an internal motivation, so something that allows the robot to take its own decision in some sense. So this is what we are actually heading toward. So trying to build a cognitive architecture that makes use of all the knowledge we have acquired in the different aspects and combine that, bringing to an autonomous agent able to interact with us in a clever way. So these are the core cognitive abilities that then we have to think of implementing on our robot. And these are the little steps that we're doing. So, for instance, we are closing the action perception loop, creating a robot yoga teacher that uses its body to show the appropriate movement and use its perception to analyze the movement, correct it, and use its body again to show you how to correct your movement. But then we are thinking of short-term and long-term memory learning, so that the robot can learn to recognize multiple people. And if we keep the yoga demo example, then can recognize that you came last time and your knee was not a good state, and so adapts its training accordingly. This might also require, for those of you who are interested in computer science, rethinking some of the learning basic mechanisms that we use in computer science. Not focusing anymore on making agents that just win against benchmark, but that can take into account in the learning process also constructs that are typical of our social interaction, like rivalry, for instance, that makes our interaction so interesting. And speaking of internal motivation, we have to start thinking of making our robot able to take their decision, to have their own goals up to a certain point. And one possibility that we are drawing inspiration from is to consider how emotions in humans serve this role as internal motivators, and so trying to model like cortisol-like internal drives for our robot. Of course, this would lead to robots that are more adaptive. At the same time, we still need to interrogate us on how to balance this out, because we don't want the robot to be just a mirror that copies us as a function of our everyday fluctuation. We want it also to be able to be consistent over time, so that we can predict what it is going to do. And this requires a very multidisciplinary discussion, from philosophy, interrogating ourselves what it means to build a self or an identity, how this is connected to our experiences during life, and then implementation side. So we are trying, for instance, to create those architectures that I was mentioning before, with multiple internal motivations fighting against each other. So the desire to interact with others on the one hand, the desire to discover novel things in the other end, the need of getting energy on another end, and, for instance, rebalancing the weight, the relevance given through these different internal drives that guide the decision of the robot could be a proxy to give the robot its own identity. But this also brings to the necessity of moving away from the traditional vision of a machine that I turn on and turn off, reaching an architecture that allows the robot to be always on, which means allowing it to learn from its everyday experience, but also being able to forget what is not needed and to prioritize what matters versus what can be forgotten and not attended. So to recap, it was a very long. So what we suggest as fundamental component of having better robots, cognitive robots in our interaction, is that we need, let's say, at least these 5 tenets. A robot that knows where to look, a robot that has a decent model of how humans, on average, function, a robot that knows how to move to be comprehensible, a robot that can adapt over time and to different needs of different individuals, but at the same time that has its own identity, making it more predictable and stable over time. This means that we need to go from making robots that are good at interacting with humans, and that's the first 3 steps, to robots that can also be adapted to you specifically, but at the same time that maintain their own self, their own identity. And I want to make a claim. So what I've showed you is mostly basic science, but it has real application. So some of this little ability that I showed you in isolation have seen application in real settings, like in collaborative robots, in companies. Some of the insights that we got from understanding how humans imitate each other and implemented on the robot led us to try and understand how this could have an impact in social spaces, for instance, applications in schools. So gathering a better understanding of how we function and how robot could function for us doesn't need then to remain in the lab. The overall goal of all this effort is to create more humane robots, which doesn't mean robots that look like humans. We use them because it's easier, but it's not our endpoint. It's robots that can perceive and understand the world like humans, that are considerate of the humans. And this could require moving away from the current paradigm of artificial intelligence, starting to think of artificial cognition instead. If you want to delve a little more with more recent results on this topic, there are plenty of events that have been organized by my students and postdocs at different conferences, and so I strongly invite you to participate and submit. Most of them are still open for submission. And if you want to have a more active participation in the field, I want to advertise also the IEEE Technical Committee in Cognitive Robotics. I'm a co-chair. What we are trying to do is really fostering multidisciplinary discussion on the topic of cognitive robotics, also to make it more relevant for the society. So join us, and all the information is on the website. And to conclude, a big thank you for your attention, and an incredible thank to all the people whose work I actually showed you today. Thank you.